consistently working late is not necessarily a sign of a hard worker, but rather than an inability to use time wisely. So, for starting a new chapter of learning, I, Anshray, being your host for today's event, want to extend a warm greeting and good evening to all of you present here. I hope you all are doing amazing. On behalf of whole SEMS family, I welcome you all for today's international webinar on the topic of a glimpse of wavelets. And to add a guest of honor and today's speaker, Naufal Ashraf, it is a great honor to have you with us. We are grateful for your presence.
Thank you. Thank you for the introduction.
Also, I see a quite number of people are joining us. Before I proceed further, let me take a brief moment for the introduction of my organization, SEMS. SEMS Welfare Foundation is non-profit entity established to work in the areas of education, social welfare, women empowerment, skills development, entrepreneurship, livelihood generation, and employability, health research, culture, international cooperation, sports, environment protection, or any other similar sectors. We promise healthy lives, a balanced and active community to and strong business. Now, let me introduce today's speakers to you all. Naufal Ashraf. Naufal Ashraf is assistant professor stage 2 in Department of Mathematics at Coaching University of Science and Technology, known as CUSAT. His administrative responsibilities as regional coordinator, Kerala for International Mathematics Olympiad, department level placement coordinator, department council secretary from 2006 to 2021, and assistant warden of hostel also. We also known as he has some publications also known as spectral analysis of singular matrices in SIMO channel is under review. Numerical solutions of partial differential equations using Dobris's filter with accuracy order 6 is published in Surveys in Mathematical and its Application 2022. Numerical solutions of nonlinear sine Gordon equation using modified cubic B-spline based differential quadrilateral method is accepted for publication in computational method for differential equations in 2022. There are many more in which a numerical solution of the hyperbolic telegraph equation using cubic B-spline based differential quadratic of high accuracy is published in computational method of differential equation 2022, and a review of minimally supported frequency wavelets is published in Australian Journal of Mathematical Analysis and Applications. There are many more. Congratulations for this, Naufal Ashraf.
Thank you. Thank you.
And we also know that you have conference publication presentations also in numerical solutions of one-dimensional hyperclovic telegraph equations using collocations of cubic B-splines communicated in the proceedings of international conference on semi-groups, algebras, and operator theories, and is under review. There is also a representation of affine group with Heisenberg operators as generators in International Conference on Analyze and its application in the Department of Mathematics and Aligarh Muslim University. Study on Hennisberg group in International Conference on Gupta's SEMS group, Semi group and Automata in the Department of Mathematics, University of Kerala. There are also a review of journals, Mathematical Reviewer, American Mathematical Society, and Paceline Journal of Mathematicals. He have also have projects supervised in MPhil from 2015 to 2021. First is approximate solutions of Fredholm integral equations with Green's type kernel in 2021. Estimations of spectral radius of refinement and subdivision operators in 2019. Refinable vector functions in 2018, and canonical dual of wavelet frame 2017. The optical coefficients in Dubéke's wavelet in 2017 and refinable splines in 2015. He also acquired many projects in MSc also from 2016 to 2021. Numerical solutions of PD using Galeckin methods in 2022, metric polynomials in 2022, singular value thresholding algorithms for matrix completion 2022, harmonic analysis on traploidic groups like 2000 in 2022, and support vector machine for data classification from in 2021, detection of sleeping spindles using Hilbert-Hong transform in 2021, and Brester's approximation theorem in 2016. Once again, congratulations for this projects and all, Naufal sir.
Thank you. Thank you. Thank you very much. So let us understand what a vector space is, first of all, we studied in our plus two classes what a vector means. So we know that. So vector means something which has a direction and a length. So that is what our basic understanding of a vector. So when I multiply this vector with a number, you can say that that multiplication is actually changing its magnitude and keeping the same direction as that of the vector. So this basic understanding we have in our plus two classes. So how do we represent this in a mathematical way? This is, if you denote this as your vector a bar, this is some scalar a m multiplied to this vector a bar. So keeps the direction same and changing its length. And you know that two vectors a bar and another vector b bar. So another vector b bar given. So that means some vector. So some vector is there, namely b bar. So how to make the addition of these two vectors? So we know we drag this b bar to the tip of a bar. So I translated or dragged this vector to the tip of a bar, and now I have the vector a bar, and you need to add this b bar to the vector a bar. So how to add? The rule of vector addition stands for this. The new vector, the sum of these two vector is a bar plus b bar is this vector. So that completes the triangle. The vector which completes the triangle when I drag this b bar to the tip of a bar. So this is a bar plus b bar. So this idea we are very much saw this in our plus two classes, or even before that in schools also we have seen this. So we have two operations, adding them and a multiplication. So this is known as addition of vectors, and this is scalar multiplication. Okay, so these are the two fundamental operations I am going to deal with. So you can now think of the collection of all vectors. So let me denote the collection of all vectors of the form x bar. So the vectors, we know what the meaning of vectors is. So now you can define the addition and the scalar multiplication. So if you look at these two operations, you can say that addition of these two things is same as this. A bar plus b bar is same as b bar plus a bar, and a lot of properties you can observe. So this addition is commutative. So you can make or interchange the roles of a bar and b bar. And you can see that if you take three vectors, a bar plus b bar plus c bar, three vectors taken, so you can associate them. That means I can make the addition of the first two first, then c bar. So this is commutativity and this is associativity. So addition has these two properties. And you can see that a vector of the kind zero vector. Zero vector means the magnitude is zero. So something which is like a point. So just no magnitude, zero magnitude, and zero direction is not specified. Zero vector. So if you add this vector to any vector, it leaves the same vector. So because of the commutativity, you can write this. So once we look at the collection of all vectors, it has this property. And if you take a bar, you can see that another vector named b bar is existing, which has the property that both the addition of these two vectors makes zero vector. Or you can see that if you have this vector a bar in hand, I can define a vector which is having the opposite direction as that of a bar. So this is minus a bar with the same magnitude as that of a bar. So if you add these two, you can say that it is like zero bar, so zero vector. So such an element exists. So if this element exists, we can say that there exists an inverse. There exists an inverse for each element in the space. So what I am trying to emphasize is I have a collection of objects named vectors, and I have an operator of addition. A rule of addition is incorporated in the set. That means you can perform addition of two objects of the kind, and you can see that the result will be a new vector of the same set. Okay, and it has these properties I have mentioned. So I'll list all the properties I have mentioned once again. First property I just mentioned is closure property. Closure property means closure property. Closure property means if you take two vectors a bar and b bar, a bar and b bar, addition makes a new vector in the same set. A bar plus b bar belongs to the set X. So let me name X as the space of vectors, space of vectors, space of vectors, or for simplicity, we can call a vector space, vector space. So this is closure property. And second property is, I have mentioned associativity. Associativity, A plus B bar plus C bar is equal to A bar plus B bar plus C bar. So this property I call as associativity. Associativity. And third property, existence of an identity element. Existence of an identity element. Identity element. That means I mentioned A bar plus 0 bar is equal to A bar. So such an element exists known as the identity, 0 bar plus A bar. So this element known as identity, especially additive identity. Additive identity. Okay, and the fourth property I mentioned is existence of inverse. Existence of inverse. That means for each A bar belongs to X, there exists a B bar from X such that A bar plus B bar is equal to this identity, zero vector. Okay, and fifth property I mentioned is commutative property. Commutative property. That means A bar plus B bar is equal to B bar plus A bar, B bar plus A bar. And also, I mentioned about the scalar multiplication. So, A bar is taken, then M A bar. This M is coming from real or some field. So I just want to mention a real field. So, M is coming from real numbers, set of all real numbers. So, I multiplied, the length is multiplied with some real number. So, now I have to look at the properties of scalar multiplication. So, if you multiply M to A bar plus B bar, this is actually A bar is a vector taken, B bar is another vector taken, A bar plus B bar is a new vector in X. So A bar plus B bar is multiplied with the M. So that is equivalent to M A bar plus M B bar. That means you can individually multiply M to each vector A bar and B bar respectively. Then you can add them. Oh, this gives you some relaxation or flexibility of interchanging the operations addition and scalar multiplication. So I call this as scalar multiplication. Scalar multiplication. Scalar multiplication. So this is what first property is. Now second property is M into A bar. M plus some other n. M plus n. So two numbers are taken. M plus n into A bar is equal to M A bar plus N A bar. And 1 is the real number 1 multiplied to A bar makes the magnitude is multiplying with 1. So that leaves A bar unchanged. Okay. And M into N multiplied to A bar is same as M into N into A bar. So these kind of flexibility in switching in between the operations, scalar multiplication and vector addition is allowed. So now we call X a set of vectors, together with this addition and a scalar multiplication, a vector space, Okay. And now I want to give one example of a vector space that I'll utilize to represent the addition of functions. So let me talk about a function defined in between closed intervals 0 and 1. So you can see that as a simple function, some function. So this is a function defined in 0 1, and it has no break. So I call this as continuous function. It is continuously flowing from one place to the other. So you may understand this as a continuous function. And if I call this as your function f, it is your function f. And another function you can think, this is your g, another function g, that is again a continuous function. So I would like to use a notation for the space of all such functions, a space of all such functions that are continuous in the interval 0 and 1, in the interval 0 and 1. Okay, so let me use a notation C01, C01, and I can define addition and a multiplication named scalar multiplication. So this is my space C01, collection of continuous functions defined in the interval 0 and 1. And I need to talk about the meaning of this object and this object. Okay, and I consider the real numbers, set of all real numbers, and alpha is coming from set of all real numbers. So this letter will be utilized to represent scalar multiplication, as I mentioned in the case of m. So I may utilize alpha as a real number to talk about the scalar multiplication of a function. So let us think how to make addition of these two functions. So let us think about a point which is in the interval 0 1, and I have to talk about f plus g of x, f plus g of x. What is the meaning of f plus g of x? So I have a function in the interval 0 1, g another function in the same interval, and x is any point, any arbitrary point in the interval, and I have to define a new function which should be in the same space. It should be in the same space, and I need a rule to talk about that object, right? So my new object will be f plus g. New object will be f, notated as f plus g. So f plus g of x is equal to fx plus g of x. What is the meaning of this? So look at x here in the interval 0 1. F of x means this height, f of x means this height, and g of x means this height from this point to this point, the length of this. So this length plus this length is added. So you can see that this length plus this much is this much. So the value of the new function at this point will be at this point. Okay, that you can see for another location. So if you choose x naught is here, this is your f of x naught, and this is your f of this is your f of x naught, and this is your g of x naught. So f of x naught plus this height, so this much height, this will be f plus g of x. So do it for all points in the domain, and you will get a new function which falls in this way, and you will get a new function in the same interval. So look at up to the interval, up to the value, so 0 to 1. So this is your addition rule of functions. Functions are added in this way. And how function is multiplying with a alpha. So I use alpha a real number, alpha f. Alpha s should be a new function, alpha f of x. Alpha of x, f of x is equal to alpha into f of x, alpha into f of x. So remember, I am considering this image for f, or f is a function from closed interval 0 1 to real number, reals. So it's a real valued function defined in the closed interval 0 1. So I can multiply alpha a real number with this real number f of x. So this multiplication is meaningful. So these two operations I can perform. Okay. So what I'm trying to emphasize is I can say that C01 together with this rule I mentioned, addition and scalar multiplication, will agree the properties of a vector space. So you can verify if you are interested. So the properties I mentioned for a vector space will be satisfied by these two operations I defined. Understood? That means the collection of all functions. So let me write f from 0 1 to r such that f is continuous. F is continuous. This is notated like C01. Satisfies is a vector space over R. It's a simple structure. Okay. Now the point is how to study these objects. That means, is there any method to study continuous functions, and what are the examples of continuous function? So as I said, if you look at 01, the this function is, I can denote this as f of x is equal to 1 for all x in the interval closed interval 01. Closed interval 01, the function takes the value 1. All domain variables or domain values are mapped to the value 1. So this is your function 1. So now I look at how f of x is equal to x looks. X for all x belongs to closed interval 01. F of x equal to x. So how that function x looks? So if you take 01, if you choose 0, the function value is 0. If you choose 1, the function value is 1. So if you mark this as your 1, and if you take half, the value is half. The value is half. If you take 1 by 4, the value is 1 by 4, like that. And if it is 3 by 4, the value is 3 by 4. So you can see that joining this, it's a straight line joining these two points. So this point is 1, 1, and this point is 0, 0 in the plane. So you can mark this a straight line, f of x is equal to x. F of x is equal to x. Okay. And if you choose f of x is equal to x square, so the plot will be something of this kind, 0 to 1. So x square. So I'm interested in looking at the interval 0 to 1. So if you choose 1, 1 square will be 1. 1 square will be 1. And if you try to plot it 1 by 2, it is not 1 by 2. The value is not 1 by 2, but it is 1 by 4. It is 1 by 4. So at 1 by 2, the value is 1 by 4. So like that. So you can see that there is a curving happens. Curving. So f of x is equal to x square. So this will be f of x is equal to x square. The graph will be like this. Like that, if you try to plot these functions, f of x is equal to x raised to n for some n belongs to the natural numbers, you can see that in the interval 01, you can see that the initial function will be constant. This is one constant. This is next is this straight line. So x is a straight line. The straight line. Then it starts curving, and if you increase your power, you can see that it again curves more and more. But the values at the end points will remain the same. So 0 raised to any number is 0. So this will be starting from 0, and 1 raised to any natural number will be again 1. So in between the values, there will be curves of this kind. So this is happening. Okay. So my point is, if you want to understand any continuous function in the interval, you can depend on these fundamental functions. Hope you understand. If you want to study any type of complex phenomena, you will be looking for fundamental functions that are easier to study, and through the informations I get on the fundamental functions, can we talk about the complex phenomena. Okay, that is a common practice in science. We will be dealing with some simpler things, and we will study the simpler things, and we utilize their structure so as to talk about the original thing, original function. So the interest is this. So can I take f, okay, and these fundamental functions I have mentioned, I can talk about the combination of these functions. So as I told you, I can add two functions. So let us talk about 1 and 1 plus x square. 1 plus x. This will make a new function. 1 plus x will be a new function. 1 plus x plus x square will be another function, another new function, right? 1 plus x square. And like that, you can think of creating new functions utilizing these fundamental functions x raised to n. These fundamental functions x raised to n. So like that, if you look at 1 plus x square, this function is different from this function, and this function is different from the third one, right? So if I look at a sequence a naught, a1, a2, etc., any finitely many real numbers I can choose. These are all real numbers, and I can take a naught times 1. That means the first function 1 is multiplied a naught times. This multiplication is scalar multiplication I mentioned in the beginning. Plus a1 times the second function, a2 times second function, a3 times x3, like that up to an times x raised to n. This produces a new object. Let me call this as Pn of x. This is our polynomial we have seen in our schools, polynomial of degree n. We call this a polynomial of degree n provided this coefficient is non-zero. This is not equal to 0, then we can call this as a polynomial. So the fundamental idea of studying any continuous function is you study the polynomial. And you can see that the sequence of polynomials can be utilized to study this. So you can see that any continuous function in the closed interval 0, 1 can be studied by utilizing this fundamental functions or polynomials. Hope you understood. Now, similar study that we practice in science and engineering. So let me move on to my slides. So the title of my talk I've given a glimpse of wavelets. I can talk about the entire literature of wavelets, but I'll give you a feel of the subject. That's all. That is what my intention. So it's an expression I have written. So I need to write. So it's a well-known theory known as Fourier series approximation. This is very popular in science and engineering. So if you have a periodic function, then that periodic function can be approximated using the well-known sine functions and cosine functions. That means if you have a periodic function with period L, fx is such a function, and you can write this as a naught by 2 plus an into cos 2 pi nx by L plus bn into sine 2 pi nx by L, where this is an infinite sum. Polynomial, I explained earlier, is a finite sum. Okay, so that is a combination of 1, x square, x cube, and so on. But here we are utilizing cosine function and sine function and the constant function. So these are the building blocks we use to represent any periodic function. Periodic means it repeats after a certain interval. For a certain interval, the function repeats. Yeah, and these coefficients an can be calculated using this integration. That means in a common man's perspective, so we are fixing your buildings or building blocks or your reference, and you are trying to analyze f. Okay, so you have to know how much each cosine function and sine function are ingredient in f. That are the informations recorded in the coefficients a0, a1, a2, etc., an, as well as b1, b2, etc., bn. So a0 by 2 tells you how much the constant function is there. So that is what the information you have to carry here, and how much the function cosine of certain level or certain oscillation will be ingredient in f, and how much the sine function is there. So those informations can be catched from the integration 0 to L f of x into cos and sine. And a naught is just integrating f between 0 and L. Okay, so one example is this: a square wave f of x is equal to this one, -1 in the interval 0 and pi by 2, and 2 in the interval pi by 2 and pi. Okay, so that can be approximated using this function. Approximated. Remember, this is a continuous function and it is periodic in nature. So that means, so -1 and 2. So f is mentioned f as, so if you look at 0 to L, this is fixed period you are talking about. So 0 to so what? So 0 to pi by 2, the function takes the value minus 1, and pi by 2 to pi, the function takes the value 2. Well, this is not 2, but this one. So if you takes this value 1, this is 2. So between this interval, the function takes the value 2. So see this, and it is assumed periodic. That means f of x plus pi is equal to f of x. That means it takes the same behavior between any interval of the same length, pi plus 3 pi by 2 and 2 pi. So in between pi and 3 pi by 2, it takes the same value as it took in the interval 0 to pi by 2, and it will take the same value in the interval 3 pi by 2 and 2 pi. So this will be the behavior in any interval of length 0 to pi. So you can say that this function is periodic in nature with period pi. This is the period pi. Okay. So remember, this function is discontinuous at pi by 2, at 3 pi by 2, at pi, etc. So this is a discontinuous function. So to analyze this, you are looking for sine function and cosine function, and your another function is constant function. So sine x, cosine of x, and the constant function 1. So how sine x behaves? If you take the interval 0 to 2 pi, sine function is oscillating. So sine 0 is 0, sine pi by 2 takes 1, and it reaches 0, sine pi is 0, and sine 3 pi by 2 is negative 1, and 2 pi is 0. So this will be the graph of sine function. So this is sine function. And cosine function is, this is just a pi by 2 translation of sine. That means, so if you look at cosine function, cos 0 is 1, cos pi by 2 is 0. So this will be 0, cos pi by 2 is 0. This is cos pi is minus 1. This is minus 1. And this is 3 pi by 2. 3 pi by 2. So shift this sine function a little to the left. You will get this function. And it continues in that way. So these two functions are periodic functions. Sine function is a periodic function. Sine function is a periodic function with the period 2 pi. Sine x plus 2 pi is same as sine x. And cos x plus 2 pi is also cos x. So these are 2 pi periodic functions. Okay. And our basic aim is to write any periodic function. It's an arbitrary periodic function using these fundamental notes. Like any music is a combination of fundamental notes, right? So any literature is a combination of alphabets like that. So we are interested in looking at any arbitrary periodic function as a combination of sines and cosines. So this is a well-known theory known as Fourier approximation, Fourier series approximation. So this is the idea. So if you take fx as an infinite sum, you cannot deal with. So you can think of an approximation that contains a few terms, say 5 terms. So that will be of this. So remember, left-hand side is a discontinuous function and the right-hand side is a nicely behaving continuous function. So you are approximating a discontinuous function with a continuous function. You can. Okay. So if you add more terms, you will get more closer approximation to the original function. So as I have shown in this figure. So here in blue letter or blue marking, that is a function that I have talked about, the function f, and the red one is the first approximation, and the other colors gives you better approximations to the original function. So this is the way you can make an approximation to any periodic function using sines and cosines. This is known as Fourier approximation. So this can be done in a discrete setting. So discrete setting in the sense you can talk about, instead of looking at a continuous function, say set of values. So that is notated like a finite number of terms, finite number of complex numbers, just a complex number, a finitely many complex numbers, and you can see this as a vector space. this as a vector space. How this Cn can be seen as a vector space? That is a next thing. So Cn I mentioned it's a collection of complex numbers. So n complex numbers. So if you take an object of Cn, it will look like z of 0, z of 1, etc. z of n minus 1, n tuple of complex numbers. Some other object from the same set I can take w0, w1, etc. wn minus 1. So I need to play with the same trick or same stuff I have mentioned in the beginning. I need a vector space structure. I need a vector space structure on Cn. So you need to define z of z plus w and an alpha, a complex number instead of a real number. So I'm multiplying a complex number to complex number. So I need a rule of scalar multiplication. So how z plus w is defined? I need an object of the same set. So you can add the component wise, add these complex numbers component wise. So z of 0 plus w of 0, etc. produce n minus 1 plus z of n minus 1. So these finitely many terms added component wise give you a rule of addition between objects of Cn. And alpha taken from C, alpha times Z, I can define alpha times Z is, remember alpha is a complex number. So this complex number is multiplied to each component, Z of 0, alpha, Z of 1, etc. alpha, Z of n minus 1. So in this way, you have the rules I have set up in the beginning on this particular setup. Okay, this new setup Cn has the structure of a complex vector space. Now I can think of the building blocks in this space, like we have seen in the case of continuous functions in the closed interval 0, 1. Polynomials can be considered as building blocks, and in the Fourier approximation, fundamental functions sine and cosines can be taken as the building blocks. And in the similar way, we need some building blocks on the space Cn to study any points, any vector in Cn. Or intention is, so set up some building blocks. So set us. So I'll conclude in 10 minutes, but I'll tell what it is. So I call this as building blocks. Say U1, U2, U3, etc. Un are building blocks. Building blocks of Cn. What is intention? If I have Z from Cn, an arbitrary element in Cn, I need to represent this one in terms of this summation, sum an into un, n from 0 to say finite dimensional, so some level n, for finitely many. So this set has finitely many elements. So intention is represent an arbitrary element in Cn, Z in Cn, in terms of these building blocks. So if you want to represent this, you must know what are these ANs. So our aim is to represent a function or a vector in Cn in this fashion using these building blocks. We must have a way to calculate this ANs. So this is the purpose. The literature of this study actually deals with this representation, but in many different variations in different setup. That's a interesting thing. So what are these ANs in a common man's perspective? So this is actually, this is the function we want to analyze. This is a function we want, or a vector we want to analyze. And these are the building blocks we have set up. And I have to know how much these building blocks are influenced to make this Z possible. So that is the field. How much this function or building blocks are inbuilt or utilized, or how much is the ingredient, or how much the building blocks are ingredient in the original function. So that is what we want to know. And you can see that this space has more structure than a vector space, more structure than a vector space. So this can be done very easily using the notion of inner product. So here the building block I set up is this. This is the building blocks e raised to 2 pi I mn by n, and what we look at is our yeah. So let me use this notation. 1 by n into e raised to 2 pi I mn is the building block. So this forms a basis for Cn. The same thing. So in the case of continuous functions, we had polynomial. In the case of periodic functions, we have sine function and cosine function. Here itself, we assume these are periodic in nature. So a finite sequence that is assumed to be periodic. And we are going to utilize the periodicity of sines and cosines to write any function, any vector z in terms of these building blocks. So that is what it means. Okay. So this is actually multiplication with a matrix. Multiplication with a matrix. So this is your input. This is your input. This input is multiplied with a matrix to produce an output. So that are the frequency informations inbuilt in a vector. Okay. So this is the technique behind Fourier approximation. And you can come from the coefficients to reconstruct the original one back. So you can switch from one vector to the other and vice versa. You can come back. So that come back means to produce z hat, you have multiplied with a matrix. And you can invert that matrix, multiply that inverse in the z hat to produce the original one. So you can go back and forth because of the invertible nature of this matrix we set up. So I think I'll stop here and I'll talk about the idea of wavelets coined in the in this direction. So wavelet means, so I'll talk about wavelet. That means these building blocks are some functions psi1, psi2, psi3, etc., psi n. These are functions. So any function f that is expressible in terms of ai psi I, where I from 1 to infinity or infinite sum if you want. So finite sum or infinite sum. So I need to represent any function, arbitrary function, utilizing a building blocks. How these building blocks are generated? So these building blocks are generated by translation of a function or a single function. So let us think of a function. So if you look at a function, this is a function. This function can be translated. Translated means t f of x is equal to f of x minus k. So let me call this as integer translates. So that means if you have this function, this is 1, 0, 1. So I am translating by 1 unit means, so at 0, this is 1, this is 2, 2, 3. If you translate this function, you will get the same function translated to the right. So drawing is bad, but see, the same function is translated to the right or to the left. Depends on the sign of k. So a single function can be built up and its possible translations can be utilized, and dilations of f. Dilation means f of some ax means if you take this function, dilating this means either stretching it or again concentrating it. So these are dilations. So the idea of wavelet means building a family of functions from a single function psi. So let me call djtk. J and k belongs to integer translates and integer dilates. So this family of building blocks have to set up, and I have to write any function with certain properties, of course, but I don't want to give more technical details. So intention is this: f needs to be approximated. F needs to be approximated using this. So a j comma k dj tk psi. J comma k belongs to z. So this kind of representation is needed. So the job is to calculate these coefficients. So wavelet means this. So let me stop here at this moment, and you can ask questions.
So I guess there was it was a very effective for our audience. That was a very good piece of webinar. Thank you, sir, for this beautiful webinar which you have conducted today related our vectors problems. Again, thank you for all your attending with today's webinar. And if you have any additional question, you can contact us by mail or telephone. We are happy to provide you additional support to you.